today I have the pleasure to host this session with my dear fellow researchers about quantum computing and give you a better impression of what's going on in Europe in research, where we might see the first utility come from quantum computing and what we need to do to get there. So with this, I don't want to hold you up any longer, and I welcome my fellow panelists on stage. That is, Tommaso, David is unfortunately not here, but we have Maria and Michele. Welcome on stage. All right, so you already know who I am, but we'll take some time to just kick this off to let these gentlemen and gentlewomen introduce themselves about what they're up to and their research, and we'll then dive into a couple of core questions. We'll also have time later on for your questions, so you might think already what interests you in quantum computing, and then we'll get into this. So let's start maybe with you, Michele. Who are you and what are you doing in quantum computing?
Yeah, thank you for the introduction. Good morning, everybody. I'm Michele Grossi. I'm a physicist. Actually, I'm a researcher at CERN in Geneva, and I'm the coordinator of the hybrid and quantum computing infrastructure. Basically, it's part of the CERN Quantum Initiative. So I will leave the introduction also to the other speakers.
So my name is Tommaso Calarco. I'm a theoretical physicist. I work on quantum control. I lead an institute at Forschungszentrum Jülich, Germany's biggest national lab. And I sort of started and I run a European initiative which with 9 billion euros is trying to build quantum computers and other technologies.
Hello everyone, my name is Ilaria Siloi and I'm a scientist, I am a researcher at the University of Padova in Italy. So my background is in quantum computing, but I worked at the interface between quantum computing and material science for some time. I spent part of my career in the US and in Europe, and I got back a couple of years ago where I'm working, and right now I'm working in the group led by Simone Montangero, and my main research interest is quantum computing, algorithms, and also applications from the industrial partners.
Very good. Now, you got an overview of who's on stage, but it might be also very good for us to just have a feeling for who's in the audience. So, to kick this off, if you heard of quantum computing, what is a qubit before? Raise your hand. Who knows what a qubit is? Okay, lovely. Who has heard of Shor's algorithm? Okay. And who has no idea whatsoever quantum computing can do and is about, and like to start from the ground? No shame. We all, started at zero sometime. Cool. Let's kick it off then in, starting with the fascination for quantum computing. Why is it so special? You could do many things in life, AI here, neuromorphic computing there. Why quantum? Maybe let's start with you. You obviously do research in quantum computing. It fascinates you. Why? Why not research anything else?
So usually I try to answer this question with a simple statement, and I say CERN is quantum by construction. What does it mean? Essentially what we do is that we study, the interaction of protons inside the Large Hadron Collider, and then the theory behind this is, if you want the standard model and whatever, you can extract from this. Essentially, it's a quantum field theory, and so the possibility of studying this kind of theory with a technology that essentially speaks the same language is somehow fascinating, and of course has a scientific motivation. And when we start this project at CERN, our idea is try to use the technology. Essentially, we are technology users and adopters, and essentially also contributors to the technology. And the idea is to understand if we can improve the way we do our analysis, the way we understand the law of nature. And it's very fascinating. Of course, we are more on the research side. We are not interested in somehow commercial application, whatever, but I think that from a foundation point of view, a research foundation point of view, it's already a good start to understand what the technology can bring to the table and how to refine the project that we are working on at CERN, but with all other institutions and research centers that we have here.
Tommaso, why quantum computing?
Why is it fascinating? Well, there are many reasons why it is fascinating. The reason I started with was that it was utterly useless, and also that it made no sense whatsoever. So Schrödinger, one of the founding fathers of quantum mechanics, wrote, he didn't say, but he wrote in the Proceedings of the Royal Academy of Sciences in London that sometimes we think that we might do experiments with individual atoms, but this is only a thought. It entails inevitably ridiculous consequences. It would be much more serious to think that we raise a pterodactyl in a zoo, and now nobody knows why he chose a pterodactyl as opposed to any word which is easier to pronounce in any language. But the reason is it makes no sense, right? You all learned in school, you do not manipulate single atoms, right? So now I brought for you one example of why it is fascinating to me. So I have one example why it is boring. This is in my left pocket. This is a kind of device which you know, I will put it here on the left table. And this is something which, like CERN, it does contain quantum, but it is actually old quantum. It is the first quantum revolution. Because without Schrödinger and all these other people, Max Planck and so on, who found quantum mechanics, which actually will be celebrated next year, is the International Year of Quantum, going to be proclaimed by UNESCO in the next few months. Without them, we would not be able to create processors, transistors, lasers, nothing. No AI, by the way, without quantum mechanics. However, this is like what was referred to before, like quantum of the first quantum revolution. Now, in my right pocket, which I will put on this table, I have another device. You have never seen this device, and you have seen it, you have not held it in your hand, because this looks very much like this one, but when I switch it on, you will see that this is a Samsung Galaxy Quantum. This is the first consumer electronic product which contains quantum technologies of the second quantum revolution. Now, it's not a quantum computer. It only contains a tiny quantum random number generator. I have it on the back, a little chip. Okay, I can show it to you afterwards. And this is a very nice story of what we do not want to happen, here in Europe. And I will tell it afterwards. It relates to the word ecosystem, which is there, which I hope is also somehow fascinating.
Very, very cool. Touching on many aspects already. Ilaria, what fascinates you about quantum computing?
Okay, I think I shared this with Tommaso. I also started studying this because it was not useful at all. It was just beautiful, which is, beauty is something that usually helps. And turns out that, aside of technological development, there is also something different. That is, as Michele mentioned, nature is intrinsically quantum. So whenever you need to simulate or rather to understand nature, you need to take into consideration its quantum nature. And Feynman was one of the first one who said that at the bottom you cannot avoid to include the quantumness of nature. And the idea is that quantum computing may helps you in not just in simulating, in actually having a living experiment of the inner and most quantum side of matter. So the side that is interesting to me is the fact that you can actually have control on degrees of freedom that usually are not controllable. And this, I think, is very fascinating.
Maybe let's unpack this a bit, as not everyone might be aware of the term degrees of freedom. So what actually means this in, very practical terms, like photons shooting around, electrons going that way? What is it tangibly?
Is the question to whom?
Ilaria, feel free to start.
Oh, degrees of freedom. Okay, imagine that you want to guide, for instance, the trajectory of a particle, or you want to guide the behavior of a system. in this sense, we are, at this moment, we are thinking of quantum systems. So when we are thinking of quantum computers, it means that you have a quantum system, and this quantum system is something that you can control. So you can control how it behaves, how it moves, and you can control the atom at the let's say, at the levels of the excitations. You can excite specific transitions in the inner levels of your atomic structure, and this is what I mean by for a practical example of degrees of freedom.
Can I make a simpler example?
Sorry.
So, okay. So this is a glass, right? So its degree of freedom is I can put it here, or I am free to put it here, okay? So this is a degree of freedom in the sense that, it can be in any position in between. Actually, it has more degrees of freedom. It actually has 5 because, I can put it, on the floor and then move it this way or this way. And these are 2 degrees of freedom. I can also rotate it. I can also put it like here. And so there are more than 3. If it would be completely wobbly, it would be many more. But since it is rigid, it is 5. So a degree of freedom means some number which describes something like where my electron is, or my glass is, or myself. So what is needed to a parameter, if you wish, which is needed to describe how something is behaving. And now, for quantum, it's a different story, but maybe we'll come back to that later.
Yeah, maybe this is also a good point to just think, why is quantum so fundamentally different? Like, why do we have these extra degrees of freedom, like variables that you can manipulate? Maybe you could talk a bit about entanglement, superposition, spin, things that don't exist in our everyday world.
We have effects that are pretty unusual, pretty not only spooky, they were defined spooky by Einstein. So. And we make use of these effects in order to build a different kind of computation, in order to build different algorithms and possibly a different computer.
Yeah, so we learned the quantum world looks very, very different from what we normally experience, even though it might be quite useful for building real-world devices. And, if you're confused, don't worry. I mean, even physicists, they don't get it. At some point you just accept it, that it's different, and that you can make calculations, and they give you results, and they make sense, and you just accept it. It works. And so you do these calculations. And that's how you, make quantum computing, in the end, hopefully useful. But before we dive into the details of quantum, you mentioned quantum technologies. And maybe just to put this into context, I mean, people throwing around there's quantum computing, there's quantum sensing, there's this and that. What is quantum useful for? What can I be, building with quantum? And why is everyone talking about quantum computing rather than, say, sensing or cryptography? Tommaso, would you like to take that one?
Well, why is everyone doing that? Well, there is one big problem. So actually, I am leading the Institute of Quantum Control, right? But what I do for a lot of my time is quantum hype control. There is a huge problem with quantum hype. And this, interestingly, is coming from industry, of all places, yeah? Because if you are someone in the research department of some big industry, you wanted to convince your C-suite, then you will have to promise that within 2 years, return on investment timeline, of course, this will change the world. And this is bullshit, yes? So there is no way that quantum computing is going to change the world anytime in the next 10 to 15 years, if at all. And well, it's good. So there is a good side of hype because it means, you motivate. And actually, it is because some people manage to convince the CEO of Google. Yes, you want? Please, correct.
You can buy a new phone if you, for example. Just there's very simple application, but of course there is nothing very effective, right? What you want to say is that
exactly. No, what I want to say is that quantum computing is a long-term perspective. And there is a lot of exaggeration about its ability to change the world in a short term, which we have to be very careful as scientists, but also as decision makers in industry and in government. And there are other branches of quantum technologies, such as communication, which are maybe less hyped. This is why, to answer your question, it's not yet so spoken so much, but which are already commercially available. And in fact, we are deploying, as we speak, a European quantum communication infrastructure, we will come back to that later, in which we are going to connect with those commercial devices all European capital cities with secure quantum communication channels. And there is also quantum sensing, which is the ability, all of this is based, as I said before, on manipulating individual quantum systems, single atoms, single electrons, single photons. If we can do that, we can also, an electron is the tiniest possible magnet, so, very tiny, and this is something which is very important for CERN, for detecting particles and so on, and also in medicine and so on. You can get very tiny signals, a very small magnetic field comes around, which nobody would notice, and the electron goes, because, it senses the tiniest disturbances. So you can use it has already been demonstrated, to sense, to measure the field generated by a single neuron in vitro, not in vivo, but a single neuron when it fires in and out. And this is useful for brain science and a lot of things, which may be also connected to the main topic of this conference. So there is really a range of applications. Fortunately, our decision makers at national level, they understand that, and we are deploying all of them. But maybe in the public discourse, this is not so much what is in the foreground, because we have sort of to keep, it seems complicated, so we have really to discuss and to inform and to take the time to switch off the quantum devices, which may disturb us.
The quantum devices, yes. Okay, so we learned, at least for now, quantum computing is utterly useless. Noted, but it might become useful in the future. Maybe let's take this vantage point and, just very briefly, you're all researchers, you're doing fancy and cool things, but very, generally, as if you were writing a proposal to get funding, how would you pitch your research project as something cool and being useful in the future? What are you doing? Very short. Give us the 2-minute elevator pitch each.
Okay, from my side, one of the interesting things are applications in quantum computing for industries. I'm following a different project in this sense, and the idea is, the thing that I think everybody knows is that in our daily life, we do optimization. We optimize many different things. We optimize schedules, we optimize traffic, we optimize portfolio, so a very different ranges of application. And this kind of optimizations relies on the exploration of many different configurations. So many times these are combinatorial problems, so they are based on arrangements of elements, and you need to look for the best arrangement. And to do this is very difficult, is most of the time an NPR problem, and quantum computing may help in this, because there are algorithms that are proven or close to be proven to work better and to have a polynomial advantage. So it is. Are
you developing these algorithms, or what is it specifically that you're looking into, just to double click on it?
So we do several stuff. The first thing is, given a problem, map the problem. So write the problem in a language that is amenable to a quantum computer. And it is already a task, a difficult task. And then you may play with algorithms that are already available and optimize them. And it is a second one. So we both, we work in both directions at the moment.
Very cool. Tommaso, what are you looking into?
So you want the 2-minute speech? So I would say that there are things which are impossible to be computed with standard supercomputers. For instance, if you want to know what a certain chemical compound will do, you develop a drug, you cannot calculate it. You have to, make this substance and test it on animals, people, and so on. But if we could calculate the effect, we would spare all of that. It would be much quicker. However, this is enormously complicated. However, on the other hand, those molecules which make that drug, they are made out of atoms. They are actually quantum objects. So I could build a quantum simulator. It is a special type of quantum computer, and we already have, some of the best results here in Europe on that. And if I build this quantum simulator, I can arrange the atoms, which I showed you in the picture, in the quantum simulator, in the same configuration that I have in my molecule. I can engineer it as to learn what are the properties of that, how it behaves, what are its effects. All computed without having to do any animal testing, any years long development. So this is quantum simulation, which at the moment is the only thing that we know that for sure, if we manage to build those machines, will actually provide this enormous acceleration. And this is what the biggest companies which are developing this hardware are focusing on. 2 minutes, yeah.
Michele?
Yeah, just want to make a small parenthesis of what we said before. Saying that something is useless is very dangerous, because I can tell you a list of examples that comes from CERN, for example, when you have indirect research product that comes from the discovery of the Higgs boson. Nobody cares about the Higgs boson if you want, right? If you go to the bar and drink an espresso, what cares? But if you now use the smartphone, you use the internet and so on, everything is related to an indirect research product for this kind of thing. So that's important to say. If you want to be very practical, here we are in a conference on artificial intelligence. The main problem is the computational power. Now, what is very fashionable are those language models that relies on billions of parameters and billions of cores, GPU and energy and so on. What we can say is a nice proposal could be to look into this in terms of quantum application of quantum computing, and then there are, so machine learning and deep learning in general is much complicated than just run algorithms. You have training, you have inference time, and then we can try to see if there is a way to compress a classical algorithm into a quantum algorithm, and then try to go to the optimization. Going back to this word is always in the word of physics. So you go to optimize the resources and try to implement a quantum machine learning in the inference stage or in the training phase of a machine learning model. So this is something that can save us in terms of computing resources and energy. So this goes into this direction, and I think this is also something that we are looking into. And then in terms of sensor and technology, we are also developing a lot of interesting stuff, and the possibility of interconnecting quantum sensors to a real quantum computer would be the way you can really connect quantum information to something that speaks about quantum stuff. But there are a lot of applications also outside CERN. For example, this summer, there was the first time that a flight was run without the standard GPS, but with a quantum sensor that was able to detect the magnetic field of the Earth. So this is a new technology that are already available now. Yeah.
So you see there are plenty of applications, from materials development to machine learning and solving optimization problems for train schedules. We just need to somewhere get there and actually unlock these applications and, so to say, make quantum computers useful. So what is your perspective on what are the main roadblocks for us getting there and having a quantum machine that is viable, not just in terms of having more compute power, but also being in very economic terms, like just a good, cost-efficient solution. What's your perspective? What's lacking? How do we get there?
What are you asking?
Tommaso, feel free to start.
Okay, so the main challenge now is to get many quantum bits, many qubits, and they have to talk to each other very precisely without errors. So this is known as the problem of scalability. Sometimes we say, so we physicists, we are socialized that engineers, if they are human, they are certainly of a much lower category. This is how we are socialized. This is what I got in my physics lessons when I was young. And exactly, and what I am preaching to my students every day, since I am a professor, is exactly the opposite. Because none of what we are seeing here would be possible without engineers. Sometimes I upset. The other day, I had in a launch meeting of a big quantum computing infrastructure in Italy. I upset the president of the National Research Institution for High Energy Physics, because I said, you have to take these devices out of the hands of physicists and give them to engineers so that something good comes out of it. Okay, so this is my stance on that, because I mean, we are going, of course, there are some ideas which came out of fundamental science, and we have to keep working on fundamental science. But the point is that you need the mindset to make these devices robust, high quality, to produce them, to connect them, and to make systems out of those. And this is really an engineering challenge in the highest possible meaning of that. It is extremely difficult, and it is the roadblock that we have to overcome. This is why we need quantum engineers. We need people with a not necessarily just a scientific mindset, which can take these different pieces and build systems out of them. That is really the main challenge that we have today. So thank you for disagreeing.
Michele, Ilaria, do you agree, or what's your perspective on what are the major roadblocks?
No, I totally agree with this. The other thing I think, that is that we need to point out is that we have very different architectures right now. So the type of figures that are needed, job figures that are needed, are very different because, again, with respect to classical computation, we have at the moment there is no a physical architecture that is already established as silicon. We have a variety. And so we need to start excluding some of them, and this is something that I think is relevant again. Yeah.
I think that's very important, and as a physicist in particular, what we do usually when we present, we have this plot when we present result especially in energy physics, what we like to do is to do what we call exclusion plot. And this is essentially what we want to do. So we want to exclude some technology for some specific use case. So we want to say, okay, this was nice, at the beginning we explored everything we have at our hands, but now is the time to go specifically into some direction for a specific use case. So I don't know exactly the answer, but what is reasonable to think is that there will be a specific technology for a specific problem. So for example, we can have superconducting qubits that are very good for optimization problem variational algorithms because of the speed or whatever. And then we can use, for example, atoms and ions for much complicated with a lot of connection all-to-all qubit. Of course, those are, let's say, not as fast as superconductive, but very precise. So you're looking for a different figure of merit. So this is very, very important. And also in terms of application, what we are very good at doing is that we can reject some idea or some technology, if you want, or some approach. This is very important because in the end we want to use the science to correct what we are doing. So apart from the hype, and this is another problem, what we have to do is to understand exactly what we need in terms of developing and so on. So that's a very important role, I think, for the scientific commission and for all the scientists. Yeah.
I see I need to stimulate some disagreement among panelists as we're way too aligned. No matter which quantum startup you're talking to, they will tell you we're solving the most important problem. Because of us, quantum computing will work, whether it's better qubits, better quantum control, more qubits, better interconnections, all of these individual things. So just to, for the sake of argument, yes, we can put more qubits in a row or in a grid, which IBM has been doing. We got 2,000 qubits, so that's great. But actually, it hasn't gotten that much more powerful in terms of quantum volume or what you can actually do with the system. Whereas on the other hand, a company called Cura out of Boston has just demonstrated logical qubits that are actually, more capable, so to say, than just a physical error-prone qubit. So just for the sake of discussion, is it really just, putting more qubits, like scaling up to larger systems, or how do we make it more useful? Tommaso.
No, but this is exactly, so this very important point is exactly the reason why before I said we need many more qubits with much higher fidelity, so much lower error rates, and with much higher precision of manipulating them, without which, we cannot achieve anything. And of course, it's always a trade-off, and indeed the IBM machines have not been so very successful in terms of breakthroughs because the errors which they have, even if they put more qubits there, but they themselves, they say, we go for low error, but with few qubits, and also we created the bigger machines, but the error is not so well controlled. But that's not enough. And indeed, the result that you just mentioned, obtained in Harvard 2 months ago, is really, putting, in this case, neutral atoms, like 3-4 years ahead of any other platforms. Because before we can have this logical, which means error-corrected quantum bits in any other platform, we will have to wait several years. Which again proves the point that Michele was making, that there is a sort of a variety, a differentiation. Sorry that I can disagree with anybody on an arbitrary number of things, but in this case, I must support what Daniele said.
Which I disagree on the name. Okay.
Michele said, exactly. What Michele said, in the sense that yes, there can be different platforms which can have different advantages, but clearly, you need both many qubits and high quality. And this is why we need those engineers to sort of solve this problem.
Maybe to just double-click on the error problem, because that's one of the major problems. Like, what are these errors? Why do we have errors? Like, normal computers, they don't have errors. So why do quantum computers have errors?
Here we really go back at the beginning of our conversation. So what are the main features of quantumness? What identifies the quantumness of a quantum system? Indeed, superposition and entanglement and quantum correlations. And you need to keep them alive during the execution of an algorithm. But the point is that keeping them alive is very difficult because there are two let's say, contradictory things that are happening at the same time. You need the environment, your quantum computer to be isolated in order to keep those quantum effects alive, but you need to interact with it. You need to look at the measurement. You need to measure it. You need to look at the outcome of your computation. So these two things has to happen in a way such that quantum effects are alive. Whenever these quantum effects vanish, you get errors. And if your errors are too frequent, so if they happen too fast, you are not even able to correct them. We have many correction protocols, as in, let's say, the quantum version of classical correction protocols. But if you have too frequent errors, you are not able to apply them.
So based on this last sentence, I would like to contradict our moderator, actually, because you said, oh, what about, classical bits are perfect and quantum bits, why are they so bad? Classical bits are far from perfect, You just don't realize that in your pocket, not only a few billion transistors sit, but also the whole, layer which does this error correction, because also classical bits are error prone. But then correcting them is non-trivial, but it can be done. Only you can make so many of them that out of the sort of error-prone bits, you can distill maybe fewer, but still very many classical bits. The same holds with quantum, but it is simply much more difficult to do that correction, exactly as Ilaria said.
Yeah, very fair point. We figured out error correction for bits, but the question is, still, how do we get to quantum error correction? What do you see, coming from the research side? What are the most promising approaches? Like, is it something around having better qubits, like Alison Bob is looking into cat qubits that might have fewer errors, or is it something like having protocols that can actually, like the surface code, correct for these errors? What do you see as promising?
Question to whom?
Yeah, if you want.
Sorry? No.
Tommaso, feel free to start.
Okay.
And maybe we can.
So, it's all of that and more, in the sense that you have to start with some physical dynamics, some materials, for instance, where you have your qubits, which have little of this decoherence, which Ilaria mentioned. You have to start with a very precise, tuning and driving, which is the control aspect that I was mentioning before that we do. For instance, it is sort of very low level. And we have also a startup which just gave a pitch over there in the startup stage doing exactly that. And then the residual errors that you have, you still have to correct them by combining those physical qubits, which they are only as good as you can make them, and then you have to combine them, like Quera and Harvard University did, in order from a few of these physical qubits to make a logical corrected qubit. And then on top of that, you have to create algorithms which, to avoid as much as possible this problem of decoherence, which is sort of running, you're running against time. You have to decompose your whole algorithm in the smallest possible number of steps. And this is about compilation. So those are different layers from really the material level up in the stack, which are all necessary to reduce the impact of those errors. So it is a very complicated problem, similar in a sense to what we have also classically, but much more difficult, because keeping a qubit alive is, as the inventor of the term qubit said a few years ago, is actually much more difficult than keeping a snowball, solid in the middle of hell.
Very nice analogy. By the way, the startup he mentioned is called Cruise with a Q, so check them out. They're actually pretty cool. Michele, anything to add on?
I mean, what you meant so far is very interesting, because people working on quantum computation, but quantum technology in general, they really have to deal with the full stack of the technology, right? So when you work in classical computation, you're writing your code, you don't care too much about what is down there. Okay, of course there are architectures, GPU, CPU, TPU, whatever you want, but you're not looking into how the transistor is put on there and which kind of operation you're operating. But essentially when you want to write a good quantum algorithm, you have to take into account all of these things. So you have, let's say, an intermediate level when you have to optimize the gate you're using for doing all this kind of computation. Then you want to understand on which hardware you are running your algorithm. So in the sense, you know that some technology provide you some what we call native gate that are more prone for some kind of computation, while other technologies are less prone for this kind of computation. And then you want to compile this, and then you want to understand, you want to say, okay, I want to run my algorithm on this qubit because after the calibration, which is another important aspect of using the real technology, which is not something you don't care when you use a laptop, you don't calibrate your computer when you open it, right? So you calibrate the device, and then maybe that qubit died for some reason because quantum mechanics is fragile, and electronics as well in particular. And then you have to move your algorithm towards on a different side of the chip. So this is something very, very interesting. And of course, from a research perspective, we are happy to contribute to work at this stage, even if some companies, of course, would like to provide you, a package that does everything for you behind the scene. But this is not what we want at the moment, because we want to control what is happening now. So this is what we are trying to do at the moment.
So if I may say, just to
Sure.
close this part, right now, even if we call them quantum computers, they are much more similar to an experiment that you are running. So where you want to have control from the top level to really the lowest one. So the experiment is what you need to keep in mind.
Okay, now I have an opportunity to contradict my colleague, so that's nice. So, and I will say yes, of course, what you say is right, as you typically start a sentence when you talk about science with a colleague. But what happens is that, as a result of the first few years of our European initiative, we now have startup companies which actually sell devices which you can buy and put it in your living room if you have a sufficiently strong electric plug, which do these things. And actually, we are procuring these machines for supercomputing centers across Europe. We start with what we call familiarly the 7 quantum sisters, which is supercomputing centers in which a quantum machine made by one of these startups as a coprocessor is located. And actually, I have been asked by the G7 of the science ministers to give a demo of exactly this thing next summer. So yes, you can also buy these things.
That's a very, very nice bridge to go from the physics and why quantum physics is, fascinating, why quantum computing might be useful, what are the roadblocks, into all these human things and interactions and, how we make it actually happen. You mentioned it's $9 billion, euros, whatever, almost the same by now. Where are they going? What are you doing with all this money? Tommaso.
Many, many, many things. So, and actually, yesterday night, I had a meeting of which I cannot disclose the content, otherwise I will have to kill all of you, but soon the content will be known, about the action plan for the Quantum Pact. The Quantum Pact is a joint declaration of the European Commission and member states, which was announced in December under the Spanish presidency, and which now we are getting all member states to sign. We are about 15 and counting. And this is exactly to answer that question. So how do we make a plan? What are the actions that need to take place? So it's more or less a 10 points plan for the next 10 years. And it starts, of course, as I said before, with basic research, because basic research is essential because it is useless. It is not essential despite of the fact that it is useless. It is necessary because if you start asking the question, should I now research this? Is it going to be useful? Okay, you can give up everything, that we are using here in terms of IT. You can give up everything. So you must do curiosity-driven research because it has no reason whatsoever other than being interesting. And this is always upstream the source of new ideas which will come out. And so this is point 1.1 of this whole plan. Then there is another important thing that we are doing, which is training, because this stuff is so kind of complicated that you need to deal with it for some time to be able to manipulate it. And as I said before, if we left it just in the hands of physicists, I'm a physicist, we are doomed, okay? So we need to get other competencies. So this is really something which only from different disciplines can work, and we need really these training programs, these bachelor, master courses, PhDs, and so on across Europe, and we have actions which are realizing that. Then what we need is also to start stimulating production. So we need an ecosystem. Ecosystem is an important word that you have there, including VC investment. Once I went to Venice Beach, it's always a good idea regardless of the purpose, and you can have different activities, as you know, on Venice Beach. But I didn't go there to smoke some interesting substances, but I went on behalf of the European Commission because they wanted me to ask the boss of Quantum Lab in Google, what can we do to stimulate a comparable level of ecosystem in Europe as we have in the US? And the answer was, you cannot, because you do not sit on a pile of cash. And then on the way back to Brussels to relay this to the Commission, I sat for dinner with the CEO then of Bosch, who is has a quantum PhD, and I said, what can I mean, certainly there are counter-arguments. And he said, no, there are no counter-arguments. He is right, because what happened, what I showed before, so before I showed this quantum thingy here, right? So, and then on the back of it, as I told you, there is a little chip, which I will now show you. So this little chip was made in Europe due to European-funded projects, very much like the World Wide Web was invented at CERN. Now, where is the cash which is coming out of that? In this case, it is sitting in South Korea because the South Koreans just bought the majority of shares in this European startup, and they are commercializing that. Where is the cash which was generated by the World Wide Web? Certainly not in Geneva, yes? But it is on the other side of the Atlantic. So how do we prevent that? We need to stimulate enterprise. We need to have, even public investment in these things. So there is a series of measures that we are taking, including a European Quantum Fund, which goes in that direction. And once we have stimulated that, then we have other things which need to happen, which is we need to make those chips. Chips, we need to make them, not be dependent on someone else. So how do we make sure about that? And to make sure about that, a few months ago, I dragged a quantum computer through the security in the European Parliament. Non-trivial. I had to promise to them that it was switched off. So, but then when I was on the other side, I put it on the desk of the rapporteur for the CHIPS Act, because there is not only the AI Act, but there has only been also been the CHIPS Act. CHIPS Act is about how do we make sure that we can still get chips after China takes Taiwan, right? So but this is semiconductor chips. But my argument is not just standard chips; it also has to be quantum chips. So I started my pitch, and the rapporteur told me, "Stop there. I don't want to hear that. Just tell me what I have to write in the law." So and with the very useful classical computing function Control-C, Control-V, he took the paragraph that I suggested, and it was voted into law a few months ago. So now we have also a line on quantum chips and pilot lines and testing and experimentation facilities and design libraries, which is going to be funded as one of these action lines, and then it goes down and down to commercialization, and also creating user communities. So one thing that we are doing up in the stack, because we discussed hardware, but then we have also to do up in the stack. I mean, many of you who are here do not care, whatsoever. Is it ions? Is it neutral atoms? I mean, why do I care, you want to use these things, for some problems. So we have to give access to these machines. This is why we are putting them in this infrastructure, which I mentioned before, such that everybody can access via supercomputing center, and they can start playing with this. And actually, the US are a little jealous. We had a workshop in Washington, D.C. with the Department of Energy, which is funding the national labs for doing that. And the only thing in which they told me, we are a little jealous of what you are doing in Europe, is on this, because they do not have a public offering of quantum computers, but they are dependent on big companies. Maybe a good thing, maybe not such a good thing. But in any case, the government is looking with some interest, towards this side of the ocean, because here we have the ability to create user communities so that above the stack, we have those users which say, why do we need that, okay? And then there is a sort of beyond levels, which is maybe more global. Like 2 years ago, based on this, I had a couple yelling sessions in the White House because I wanted to have a working group on quantum in the Trade and Technology Council, which is this dialogue between US and EU on all sorts of technology. In the beginning, they didn't want to have quantum. Now we have it. And so this is also kind of bringing together the global dimension in so-called like-minded countries to create these kind of measures also at global level. And then I can go into details, but maybe I took already 5 minutes or so.
That was already quite some speech. Thanks for the overview. Maybe, Michele, to start with you and then go to Ilaria. What has been your experience with funding quantum research, but also spin-outs on a national, but then also on a more global and European level?
In our case at CERN, the situation is a little bit different because we are also a research center that is funded actually by the member states. So essentially, we get direction from each member state. So essentially, it's not easy to say something that essentially is okay for every member state. But once we, let's say, try to discuss the importance of having also some kind of development at CERN, because what we proved during the last decades is that we are able to do interesting stuff, essentially, if you want to go into the details. But what we tried to do at the beginning, so I'm talking about 3 years ago, is to set up this quantum technology initiative that essentially spread about sensors, cryptography, and also quantum computation and sensing. So we explore all of these areas. We try to say something about why it's so useful for the high-energy physics community and beyond. And then after 3 years, we reconvene with the member state, the council, and they agree that what we did was very interesting. We also helped and we discussed with each country members their initiative, because as far as we know, every member state, every country has a proper quantum initiative. So essentially what we do is try to do some suggestion and take some suggestion from there. It's a good interaction. And what we want to do now for the next 3 to 5 years is to go into some specific area of quantum technology, quantum computing, and to build something that is very helpful for the community as a first stage. So, for example, we will do some study about quantum algorithms integrating with the high-performance computing center, something about quantum sensors, and also communication. So this initiative will be more focused on specific tasks, and this is the way we try to convince the scientific board at CERN and the council that it deserves the money we got for this kind of activity. So this is how it happens for a non-government representative like we are, right?
Ilaria, what has been your experience?
Yeah, I mean, I can mention something about the Italian, the national Italian initiative. Basically, with the National Plan for Resilience and I always recovery. Sorry, guys. Quantum technologies and quantum computing has become a strategic area too. So there are basically two lines, two big institutions that have been funded in the past year. Last year and for the next year, I guess, so 3 years. One is a national center for big data, quantum, and high-performance computing. So again, here we go back to the idea that Tommaso was mentioning before, so where quantum computer will work and will act together with HPC Center. So Padova, actually my university where I work, is co-coordinating this initiative. And this is a kind of a huge one in the sense that there are 10 different tables, but one is specifically dedicated to quantum computing. And let's say the fundings in that area went already in buying Leonardo, which is the fourth cluster, the biggest, the fourth cluster in the world. And in the meantime, there will be also a quantum computer, possibly from Pascal, I guess, that will work together and in tandem with Leonardo. And also there is also another initiative that actually is more on the fundamental quantum science, and again, it is developed with the PNRR. Yeah.
That's an important message. So quantum computer in general will never work alone. So it's important to invest in both directions, right? So in terms of hybrid algorithm, but also when we talk about error correction, everything is done at a post-process. So we get information out of the quantum computer, but then we need a lot of classical computational power to correct what we had. So it's very important.
Yeah, having gotten an overview of different funding schemes on a national and more European level, how do you view these public-private partnerships or university spin-outs, and how do they, become a thing of their own rather than, after 2 years being bought by a chemical company? So, what has been your experience working with startups and, having these public-private arrangements?
Well, it is much more difficult in this continent than in the US, because there are a lot of regulations which sort of are slowing down. This is everyone's experience, and so being competitive means being quick, and I'm not saying that regulations are a bad thing, and I'm not drawing the conclusion that there should not be regulations, but just I observe that the presence of regulations which is in this continent is making it very difficult for startups sort of to accelerate sufficiently fast, as well as we do not have, what Harmut Neven, the Google boss, said, you do not sit on a pile of cash, is true. So it's not like our big industry would not have the vision to do that, but simply the huge profit margins, which big companies in the US after the internet revolution can count on in order to risk some of that for some high risk, high gain thing. They are not available in this continent, and this is where we really need the sort of public intervention, so to say. This is at the moment the bottleneck, not so much to start up, but really to scale up. So it's a much bigger challenge in this continent for scale-ups than over there. And this will determine whether we will fall back into being dependent on buying hardware from outside Europe, or whether we will this time kind of make it. We are still on time, but the train is leaving, and we really have to work hard to get there.
Michele, how does CERN work with startups? I know you have a dedicated startup program.
Exactly. We have a specific division, if you want, inside CERN called Knowledge Transfer that essentially works in improving the relationship between pure research projects from CERN and the connection to the industry outside, in particular with startups. And what happens usually is that there are a lot of interesting ideas and people that are supported to spin up some startups and companies, and this works very well. And on the other way around, there are companies that reach out to CERN, to knowledge transfer, to understand if we can do something together. And this is very helpful because beyond the national program, national funding, it's important also to have some funding from external companies. So in our case, we have external funding for PhD students, master students, and some of the summer program are paid by companies. That's an important point of view because on the one hand, you can have money essentially and resources to improve and enlarge your research program. And on the other hand, you can also give what is very important and somehow missing in many academics, the possibility to let the students knows the industry environment, the way something can happen after he graduates or finish the program. So it's a very interesting combination, and as far as my experience, I can tell this is very positive overall, and all the companies as students are doing very interesting stuff.
Ilaria, what has been your experience working with companies or guiding students towards spin-out?
I think that at least from my perspective, the National Center funded by the PNRR has this, so the interaction with companies as one of the main goal. Indeed, the entities included counts to 50, and 15 of them are companies. And even in my everyday experience, this was actually a moment to get in touch with different companies that I've never thought before they could be interested in quantum stuff. And this is what's happening. So we talk to them, we try to establish, at least a list of problems that might be interesting for them, and then we start working with students, PhD, and so on. So I think it's really a good interaction and a good chance from both sides.
Yeah, very, very nice overview. Now that you survived 1 hour of listening to this panel, I think it's a very good point to open it up in case you have thought of any questions that you would really love to know before we end this in about half an hour. So we've got like decent 20, 25 minutes left for questions. Who's got a question? Yes. Giovanni, please.
Thanks. So from an outside point of view, it looks like you're tackling a very, very big problem that for solving it, you need a lot of cash and a lot of skills. However, for solving this problem, you have, I guess, an organization issue, meaning that who can count on a lot of cash has multiple stakeholders, and instead, the one that have little cash, okay, have maybe just one owner of the project. My question is, how can we compete as CERN, as a European Union, or as a university, or as a country, a small country like Italy, with a country like China that is both very large, so has a lot of resources, but also very few stakeholders? I mean, how can you set a strategy if you have 27 countries that decide on what the priorities are? We've just said that there are so many different, we said that quantum technology is a very wide thing and there are many different problems you can tackle. Who is going to decide what are the priorities to follow, and who is going to decide the resources to make, and will the resources be available for doing it? I see a strategy problem here, like real big, compared to our, other countries, like suppose China, where they have lots of resources, very few stakeholders.
Well, it's not so much a strategy problem. Well, yes, it is a strategy problem, but it is solvable. There are different ways to solve it. You can have a dictatorship, and this has some advantages, okay, which may be like the rapidity. It is not necessarily the stability, okay? This is, of course, the big challenge, okay, because you are up against a dictatorship, which is also not really necessarily, abiding by the rule of law, for instance, or stuff like that. So this is a problem. So how can you cope? Well, but having many stakeholders does not necessarily mean slowing down. So if you would use democracy, you would be slowed down, because democracy is the rule in which the half plus one wins and half minus one spends their time to block the decisions of half plus one, yeah, as we see in many countries. Instead, what we do in our case is we never take a vote on anything. We use a different decision model, which is based on, broadly speaking, you could say consensus, in the sense that we iterate our strategy documents until, this is acceptable and supported by all relevant voices in the community. And this, on paper, sounds something which will never converges, and actually it is a method which converges much, much more quickly than democracy, as a matter of fact. And everybody is involved. There is a name for this. It is called sociocracy, and there is bibliography on that. You're welcome to look at that. And it works much quicker, because once you made a decision, then you are sure that there is support. What does it mean? That when we go to council, there are 27 member states. And then a typical discussion in Council of the European Union is that some member states say, no, I don't like that, and you never converge. And in our case, okay, what happens? It has happened many times, and this is the reason why this flagship is still alive, and the other two, which were started 10 years ago, are no longer, is that when you go there with a proposition, there will be the German representative from big fat country, which will say, we support this. And there will be the Latvian lady, which will stand up and say, and by the way, I know that quantum information theory is very important because algorithms are essential. And why so? Because the strategy which we formulate, which is going to be released actually next week, the next iteration is called the Strategic Research and Industry Agenda, has been prepared with all stakeholders. It took a few months, and now it is something which you can count blindly. Anybody whom you ask, from governments or industry or academia, they will say, yes, we acknowledge that. This is what we want to do. This is why we managed to get this quantum declaration signed by all of them, And because we build it with a sort of some engineering, I mean, there is cybernetics behind this kind of approach to decision making, so that there is really some serious theory behind, but we build it from the bottom up in such a way that everybody can find that this is what they want, because it is built based on what they want, and it is not top down. So yes, it is a challenge. Yes, engineering helps to solve it. It's control theory.
Anyone likes to add? Okay. No. Okay, so I guess bottom line, we're better at collaborating, and I guess, yeah, that's a valid argument. We got another question? Yes, please.
Thank you. Hello. I was wondering, how can you help me or scale up life system, it's called. It's within the health sector. Helps prevent illness or pathologies before they occur, or helps cure illnesses, but it's forbidden to say it. It's regulation. It's not a medical device, it's a well-being device. So there's not had enough funds for scientific research, and it's a problem for us as practitioners. Please.
So my colleagues asked to repeat the question.
Okay, sorry. I work with the life system. It's here in the box, and it's like a quantum machine that you get connected to with harness.
You said a quantum machine?
Yes.
Oh,
it's not quantum computer, but machine.
Oh, okay. And how does it work?
And it works when you look at it or when you don't look at it.
Yes.
There is an impact following.
This is what I call snake oil. Okay.
Yeah. And
this is a classical example of snake oil.
Snake oil?
Snake oil.
Okay.
Yeah. So I think everybody who is in the industry understands that. So I have no help for that. Sorry.
Okay. I'm just wondering about. Okay. Thank you.
Yeah. Okay, some more questions.
From my perspective, the great appeal of quantum computing is the ability to solve the Schrödinger equations. Am I right? With a sufficient number of electrons.
That is the great ability of a quantum simulator, which is a special case of quantum computer, which is a quantum computer which is, specialized to doing that. But quantum computers, in general, can also be able to solve other kinds of problems.
Sure.
A few of them, but not just the Schrödinger equation.
This problem is fundamental for drug development, for example. Yes. However, having said that, if I look, I'm doing machine learning, and so I looked at things like penny lane. But invariably, even if I look at the simplest network, I struggle to get a grasp of how it's actually implemented. There are maybe demonstration notebooks that show how to implement that on a simulator. However, I find it very difficult. So I can imagine that, like I said before, there are great applications, but there is a gap, an understanding gap.
Yes, and it is not your fault. It is ours. Yeah, that this gap is there.
Well, I don't know.
This is what I said before, because this stuff is very inherently different from classical programming, and so we really have to go a long way in terms of like educating, developing material which enables people who do not have a physics training to really play with this. Part of the reason is inherent because you do not have general programming principles for quantum machines. So it's really a different stuff for which we have no systematics. Maybe it exists, maybe we will develop, maybe it doesn't exist, we have to find out. But certainly you are very right in acknowledging this gap, and filling this gap is one of the important challenges in upskilling, reskilling, in order to be able to get competence of people like yourself, to contribute, to challenge what quantum machines can do, and to develop it further. So this is one of the important bottlenecks on the skill side.
And if I can complement this, we have a specific competence center at CERN in the Quantum Initiative to help with the training of the people coming from different backgrounds. Because in the end, what we understand is that quantum technology is not just for physicists or engineers. What we need is people from different disciplines, because they also come with different perspectives, different point of view, and different skills, of course. So it's of course very important, but something is already happening in different countries. We have specific master courses, doctoral school, also something in the bachelor's, when we have courses that are very multidisciplinary, so you can get information out of it.
Yeah, the other thing that I may add is that, for instance, there are companies that allows you to play with quantum computers on the cloud. And it is something that is, in my opinion, very relevant, because it makes it more closer to you. You can really at least start to see what an entangled state is. And moreover, I mean, there are many textbooks with like Jupyter notebooks to start playing with a language that is the language that you need to use to talk to quantum computers, which it's true, there isn't only one, but there is a main one. And so at the high level, basically, I mean, there are different ways in which you can play with quantum computers, but I mean, it's something that you can really learn fast, at least from, let's say, the implementation point of view, not from the physics side.
Yeah, I think that's a really important point, because on the one hand, the physicists, they need to learn about computing and about IT and basically the computer science part, while on the other hand, all the programmers, they now need to learn about quantum mechanics and all these weird physics effects. And so you need to bridge this education gap. And at the moment, there's an actual gap. Like, one of the major modes of a quantum startup is the amount of talent they can attract. Because if you have 100 quantum developers, your competing quantum startup has a really hard time also having 100 quantum developers. So yes, but we'll fix this. Any more questions? Yes. Yes, please.
I wanted to bounce on the point that you made, Ilaria. So I'm a machine learning practitioner, and would like to play with those Python Jupyter notebooks, software libraries, and get to play with get to play with concepts and stuff. But what's the point today to waste my time on this, to phrase it provocatively, if this is not going to be baked before 10, 15 years, where all the paradigms might just as well have changed? Why should I do that today?
Because you don't want to be there when it happens, and everybody else can, and you don't.
And you think, so you're stating implicitly that the things that are out today, and I've approached very few of them, I don't know them well enough, but the sort of, notebooks, libraries, simulation environments, everything, these, you reckon, are not going to evolve over the next 10 to 15 years in ways that make them unrecognizable, and therefore skills that I have acquired today would be useless in 10 to 15 years? Is this the implicit assumption?
Yes. I am stating that there is not a production, commercial, industrial advantage to be expected from any quantum computer before 10 years. It is not my opinion. It is according to the process that I said before. You will see it in this strategic research and industry agenda, which we are going to publish in next week, actually. And there are some scientific problems, like you can use a quantum simulator already. There is quantum advantage, meaning a quantum a simulator being able to solve a problem which no classical supercomputer can ever possibly solve for some very specific problems of Hamiltonian properties of some exotic physical models, which probably, with good reasons, are not going to interest you, and they have no commercial interest. They have purely scientific interest. We do not expect, it's very important, we do not expect commercial production advantage before 10 years.
Yeah. But also what happens also in the past, if you look at a different, but let's say similar field, machine learning AI, if you didn't have the backthrough of backpropagation of the possibility to use GPU or whatever, it's something that you can ask the same question 10 years or 20 years ago. And what you can do with this? I mean, everything can happen in research. It happens a few months ago that someone came up with, let's say, a more efficient algorithm with respect to the Shor's one. So Shor's algorithm for cryptography now needs more or less millions of qubits to break the cryptography. So everyone say, okay, we are safe, whatever you want. But then you have two problems. First of all is that in 10 years, when you have a computer that maybe can do that, you can go back to the things you didn't put in the right cryptography way, then everything can be taken. And on the other way around, if someone else comes with an algorithm that works with 10,000 qubits in a year, then there is a problem, because you don't know how to deal with that, and you are not prepared for this kind of technology. So I think that in general, it's important to be updated with this technology, because this is what happens also in the classical AI. We are not talking about large language models today if we didn't have the breakthrough of backpropagation and GPU. So this is something that we are expecting.
So the same question was asked. So a few months ago, the reason why I was asked by the cabinet of Commissioner Breton to draft this 10 points plan was that in last spring, I went to the commissioner. I used to play this game. So whenever some friend gets a Nobel Prize, I go to the European Commission. Then there is a photo shooting, some handshaking, and the politician also for a few minutes listens to what the Nobel Prize has to say. And there is value in that. So in this case, the commissioner asked the same question that you asked. And Alain Aspect said, well, we do not know if it will work. But if it will, we want to be ready.
Just imagine if Einstein said this at this time, or Edison, or I don't know, other scientists. Do you think that we can have all what we can use
Well, it is known that we don't know. You know what Faraday said to the Chancellor of the Exchequer, the British finance minister, when Faraday was explaining to him the wonders of electricity, and the Chancellor of the Exchequer was utterly bored. And Faraday said, but sir, one day you might be able to tax it.
Yeah, I have a trivial question. You showed the quantum chipset, and that has been produced, shipped, and sold. So can you tell us something around the chipset?
Oh, yes. This is a photonics chip. It is a quantum random number generator. It is not doing quantum computing. It's not doing quantum communication, as I said before. It generates random numbers which are used for classical encryption. And it does in essentially generating individual photons, okay, and then measuring them. And you can have photon sources and photon detectors nowadays integrated on a little chip. When I was young, this took the good part of a couple of dinner tables, okay, and just with all equipment, and now it can just be miniaturized. So it's photonics. So photonics integrated chips working at the quantum level, at the single photon level, is something which is one very important enabling technology. And it is the subject of intense discussion also in the context of CHIPS Act. And I mean, we had yesterday a meeting with the 27 member states about implementation, and this is one of the things that are going to be brought forward.
Thank you.
Welcome.
Okay. No more questions left? And also in one question. Okay, quick question, and I think in the interest of time we'll wrap up.
Very short question. So I have heard a lot about the speed of the future quantum computers, because it's said that using this entanglement technique from quantum mechanics, that these computers are much faster than an ordinary one. And I would like to know if this is true or just an hype or a weird idea.
That is true for specific problems. I will give you an example which doesn't work, but gives you an idea. When I'm in a labyrinth, I want to get out. I will try, I hit a wall, I say, now do I go left, do I go right, 0, 1, and then I try, then I do not get out. I come back and say, I went right, I should have gone left, and I try the next one. I can try all solutions one after the other. Now, if I have quantum bits, instead of 0 or 1, I can encode the 0 and 1. At the same time, in parallel, I can explore all possibilities. So this is called quantum parallelism, and the state of my quantum computer while doing that would be an entangled state, meaning a superposition of many possibilities. However, this is useless, as I said, because this is not a good algorithm, because when I read this, I will see only one of the possibilities, because my system collapses, the wave function collapse, whatever. It's a property of quantum systems, so I cannot get the right solution, but maybe I get a wrong solution. A quantum algorithm is something which masters the subtle art of having these multiple things entangled with each other during the computation, and at the end, I converge to something which I can read. And we know only very few examples of that. And this is why we need people like the gentleman seated in the first row to kind of approach a little bit more, or even the other questions that the machine learning expert here, to sort of, get to know more of this, to find more algorithms, because as I said, we do not have a systematic way to program this. The algorithms that we know, they work more or less in a magic way. You look at it, you say, "Buh." And you ask Peter Shor, who invented it, how did you make it? And he says, more or less, I don't know.
Yeah, I didn't realize it was for this. Yes, exactly.
Very, very cool. We've covered a lot of ground and we're almost out of time. As for the very last question of this panel, if you had one wish for the next 5 years of what you would wish to see in quantum computing, might it be a research breakthrough, more government funding, more collaboration, or China collapsing? What would it be? Michele.
I mean, in my case, want to find a quantum machine learning that really outperform in a specific setting some machine learning stuff for energy physics. I mean, it's humble, but maybe out of it we can get interesting stuff for other disciplines.
Tommaso.
I want a global alliance of communities and governments to make this a reality across the globe, and I'm actually working on that.
Ilaria.
I would like to see some quantum advantage for material science and quantum chemistry.
Very, very cool. With this, thank you so much for your attention and coming to this session, and we'll be at your disposal if you have any more questions. Thank you.